Welcome to the exam review of the UK Actuarial Profession's CT3 exam paper for April 2013. I'm John Lee, a tutor from ASET, the actuarial education company, which provides tuition on behalf of the actuarial profession. In this video, we'll give a brief overview of each of the questions on this paper. If you'd like more detailed solutions, then please refer to our ASET, which stands for ACTED Solutions and Exam Technique, which give both model and alternative solutions, as well as a thorough explanation of all the steps. This will be available from our e-store in August 2013, in time for students' preparation for the September 2013 exam. Well, this paper kicks off with an incredibly straightforward question on mean, median, mode and standard deviation. Frankly, if students couldn't get all of these 5 marks, they're in the wrong profession. So let's move straight on to question 2, where it all goes horribly wrong. In here we have U comes from a uniform 0-1 distribution, and F comes from F is the cumulative distribution function from a standard normal, and we need to show that the random variable x equal to the inverse of f of u has a standard normal. Well, we can see that this is a rearrangement of u is equal to f of x, which is what we did when we were simulating values from the distribution of x. However, as to the proof, there's nothing in the notes on this. It is actually given in CT6, but given that we're doing CT3, that's not very helpful to us. In the notes, there are 2 ways of proving distributions. One is to use MGFs, and the other is to use something called functions of a random variable, which is covered at the end of Chapter 3. Given that this is so odd, I'm just going to go through the basics of it now. In that, you would consider the distribution function of x, which is equal to the probability that x is less than or equal to little x. Now we will substitute in our x here, and then by inverting both sides of this, we get u is less than or equal to the distribution function of x. Now given that u is from a standard normal, we can work out this probability. And in fact, it turns out to just be f of x. So what we're saying is the distribution function of this random variable x is equal to the distribution function of a standard normal. Therefore, x must have a standard normal distribution. Frankly, I suspect most students wouldn't have had a clue what to do here and would have just shoved on and lost the 3 marks. Well, hopefully it's no big deal. Well, after the disastrous question 2, we get on to an incredibly simple question 3. Here we're giving a discrete random variable and it's CDF. Now the CDF are the cumulative probabilities. It's easy to work out the probability function of 0.5, 0.2, 0.15, 0.1 and 0.05. And then from there, it's trivial to get the following 7 marks. But hey, we're happy to take these. Question 4 is testing random samples from Chapter 9 of the notes. It's a little bit odd, as it boils down to stating stuff which you may have thought is downright obvious. So for example, in part 1 you have to define what is a random sample, which we've never had to do before. But as long as you remember to say independent and identically distributed from this distribution, then you would have been fine. In part 2, it says state what is known about the distributions of x bar and s squared in this case. So all you're having to do is regurgitate the results from the notes. Don't miss out to write a comment on the dependencies. So all you had to do is quote the fact from Chapter 9 that it says they're independent. Part 3 asks us to define the t-distribution, so for students who sat our mock, they would have been delighted, because that was our first question. A t-distribution with k degrees of freedom is basically a standard normal distribution over the square root of a chi-squared k divided by k. Yeah, I know my notation's bad, but you get the idea. And explain its relationship between x bar and s squared, well, all you have to do is regurgitate the formula from page 22 of the tables. Odd question, but should have been straightforward, as you were simply just quoting results. Now on to question 5, which is where we have 2 Poisson processes, and we're getting a 90% confidence for the difference between them. This marks the first time that a 2-sample Poisson confidence interval has been tested. So presumably you would have just recalled the formula from Chapter 11, and then applied it. However, the problem here is what is n1 and n2, and so how can we work out the mean x1 bar and x2 bar? Well, the confusion stems from the fact that we only have 1 year's worth of data from each of the 2 countries. So in fact n1 and n2 are both 1, and so lambda 1 hat is equal to the mean of one result, which is that one result, 123. And lambda 2 hat is the mean of the one result from the second country, which is 111. And if you did that, you would have been fine. Alternatively, you could have developed this from scratch. Question 6 tests confidence intervals on a single binomial. For students that have attended tutorials or watched the online classroom, they'll be aware that the key word is proportion, which tells us that we're doing a confidence interval on the p from a binomial p. And part 1 asks us to calculate an approximate confidence interval, so we'll be using that normal approximation formula. In part 2 we have to comment on the validity of this, or we're going to comment whether the normal approximation is valid, so whether the n is large, or if you remember from chapter 8 where we were doing normal approximations of a binomial, we required np and nq to be large. In part 3 we're going to explain what happens to the confidence interval as the sample gets larger. Hopefully your statistical sense will tell you that larger sample size mean that we're more confident in our results, and so the confidence interval will be narrower. However, it does ask us to explain this, so simply saying it's narrower won't get you the mark. The best way to do this is to consider what happens to n in the formula. In question 7, we're inspecting policies to find those which have claims, and we're asked to determine the number of policies we would expect to examine before finding 5 claims. Well, there's 2 ways of approaching this. We're told that 10% of policies have 1 claim. That is, 1 in 10 policies will be found to have 1 claim. And so you'd expect to examine 10 policies on average in order to get 1 policy which has a claim. And so in order to get 5 claims, you'll need to look at 50 policies. The alternative way of doing this is to realise actually it's a negative binomial with k equal to 5 and p equal to 10%. We then just look up the expected value of that distribution from the tables. In part 2 we have to find the mean and variance of these 5 claim amounts. My goodness, we're getting another 3 marks for working out sample mean and sample variance. Enjoy! And in the final part, we have to estimate parameters from a gamma distribution using the method of moments. Well, there are 2 parameters to estimate, so we need to use 2 formulae. We'll take our sample mean from part 2 and stick it equal to the theoretical mean of a gamma distribution, and we'll take our sample variance from part 2 and stick it equal to our theoretical variance of a gamma distribution. A little bit of rearranging, and you get your alpha and lambda. Question 8 tests analysis of variance from chapter 14 of the note. And it's identical, and by identical I mean the same numbers, as the ANOVA question in April 2003 question 10. However, in part 1 of this, where we're carrying out the analysis of variance test, we get more marks and actually have to do less. Well, enjoy. All the figures are given in the ANOVA table, so you simply have to divide the 2 MSS figures to get your F statistic, and then draw your conclusion. However, don't miss out the mark, which is for stating the hypothesis of the test. In part 2, we're comparing just the means from 2 of the regions, and we're going to carry out a 95% confidence interval. This kind of question has been asked loads before. All we'll do is take the formula from page 22 of the notes, but instead of using the pooled sample variance, based on the 2 regions, we actually use the sample variance from all the regions, sigma hat, the formula for which is given on page 26 of the tables. And this means our t distribution will have n minus k degrees of freedom. Part 2b is the classic comment, where we've done an analysis of variance test, and a test between 2 of the means, and in one of them we found no significant difference, and in the other we have, and we're going to have to explain that dichotomy. It's been asked a number of times now, so well-prepared candidates will be able to wheel out a standard response. Question 9 involves observing monkeys and banana eating, and frankly can be a little bit confusing. The key is to note that each monkey can take a maximum of 7 bananas. So in our first group, where we have 6 monkeys, that means they could take a maximum of 42 bananas. In our second group of 11 monkeys, they could take a maximum of 66 bananas. In part 1a, we're going to estimate the value of p, assuming that both groups have the same value of p. So altogether we have 17 monkeys, which can eat a maximum of 17 times 7, which is 119 bananas. And altogether, they ate 70 bananas out of 119, and that will give us our estimate. In part 1b, we're carrying out a hypothesis test on the difference of the 2 proportions. So quoting the formula from chapter 12, we just now need to substitute our values in. Note that the denominator used the pooled estimator of P and Q, which is in fact what we worked out in part 1a. In part 2, we're going to carry out maximum likelihood estimation, but we're assuming the probability of getting a banana is theta for group A and 2 theta for group B. Again, this is possibly a little confusing, but essentially the likelihood is the probability of observing our sample results. The probability of obtaining 33 bananas from the first group times by the probability of the second group obtaining 37 bananas, where XA is a binomial, 42 theta, because remember each monkey can take a maximum of 7 bananas, so 6 monkeys is 42 bananas, and XB has a binomial 77, 2 theta distribution, as there are 11 monkeys, and again each monkey can take 7 bananas. But at worst, if you can't get this, you can just pick up that result, differentiate it, set it equal to 0 to get your maximum likelihood estimate. The last part of the question asks us to compare the fit of the two models by considering the expected number of bananas taken in each of the groups, i.e. the mean of each of the binomial models in part 1 and in part 2, and then you'll see which fits better, and then chat about why this is true. So after the rather messy question 9, 10 is where many students started losing the plot. I appreciate I've shrunk it to try and squeeze it on the screen, but let's chat through what's going on here. This question is testing compound distributions from chapter 7 of the notes. And essentially what we have here is that S is a compound Poisson distribution, where the claims are given by Yi, but then Yi is also a compound distribution, with the claims having mean mu and variance sigma squared. So we have a compound distribution of a compound distribution. This could be a little sticky. Well, what are we asked to calculate here? We're asked to get the mean and variance of Yi. Well, Yi, as I said, is simply a compound Poisson. And so all you're going to do is use the mean and variance formula for a compound distribution given on page 16 of the tables. So for example, E of Yi will equal E of Ni times E of Xi. Once you've got the mean and variance for Yi, you're going to then use those in part 2. S is also a compound Poisson, and so to obtain the mean and variance of S, we will again use the compound distribution formulae given on page 16 of the tables. For example, E of S will equal E of M times E of Y. Although this question took a little getting your head around, it was just straightforward application of the formulae. Well, if you thought that was bad, part 3 then gets a little bit more odd. We're asked to show that the probability of Xij less than X plus C given Xij is more than C is equal to the probability of Xij is less than or equal to X. Don't freak out here, it's just simply a conditional probability. And recall that the probability of A given B is equal to the probability of A and B over the probability of B. So in this particular case, we'll have the probability of Xij is less than or equal to X plus C and Xij is more than C, all over the probability of Xij is more than C. Well, the numerator simplifies to the probability that Xij lies between C and X plus C. And we're told in the question, though it's not on the screen here, that Xij has an exponential with mean 1. We can then work out these probabilities and show it's equivalent to the probability Xij is less than or equal to X. And now the final part of this rather messy question. We've got the compound distribution of a compound distribution again, but this time we're adjusting the Xij's to create something called Xij star. And then we talk about Ni star being the number of non-zero Xij stars. And we say that the Ni stars are Poisson lambda stars, and we're asked to find out what lambda star is. Well, by this point your head might be spinning. In slow-mo, we are saying that Ni is a Poisson lambda, but we're told lambda is 1000. Now Ni star is Poisson lambda star, and Ni star is the number of non-zero Xij star amounts. Well, they'll be non-zero if Xij is greater than or equal to 2. And the lambda star is going to be the mean number of Xij greater than 2 results we're going to expect to see. So here's the probability of one of the Xij stars being non-zero, but we've got 1000 of them, and this will give us our lambda star of 135.3. Part B, where you're asked to explain the distribution of Xij star, is just going to simply use the result that you calculated in part 3 of the question. And then the final part, the mean and variance of SR, is just going to use that compound result that you obtained in part 2 of the question, together with the results you've just obtained in parts A and B. But I appreciate for many students this may have been a step too far. The final question of the paper tests both linear regression from chapter 13 and chi-squared goodness of fit tests from chapter 12, and in fact is a direct copy of the question from September 2002 question 13, with exactly the same values. It's just got slightly less marks for the chi-squared goodness of fit test and slightly more for the linear regression. So here we have a rather complicated table of results. And we need to estimate the probability of having this disease, assuming that the probability is the same for all the age groups. Well, all you have to do is total up the number of people having the disease in all of the groups, which is 43, and total up the number of people in all of the groups altogether, which is 100. And so our estimate for the probability of having this disease will be 43 out of 100. In part 2, we have to construct an 8x2 contingency table to test that there's no difference in the probability of having the disease for different age groups. Now, it may be tempting to use the P you just calculated in part 1 and carry out a chi-squared goodness of fit test with that P. Whilst this actually gives the same expected values, the question very clearly asks us to construct a contingency table. And that simply tests that there's no association between the two variables. Now in this case, the 8x2 table will be the 8 age groups along one way and the yes or no contracted disease along the other way. You're then going to have to work out the 16 expected values and compare that with the 16 actual values and use your chi-squared goodness of fit tests. So this is going to be a quite time-consuming calculation. In the final part, we're doing our linear regression using the y values against the x values. First of all, you have to draw a scatter plot using the graph paper provided and comment on the appropriateness. Well, you just need to simply say, is there a linear relationship between y and x or not? In part B, we have to calculate the fitted regression line of y on x, which is y hat is alpha hat plus beta hat times x. So you'll need to calculate your alpha hat and beta hat using the formulae given on page 24 of the tables. This should be fairly standard stuff. The only confusion might be the n is 8, as we have 8 points on our graph, which isn't the n in this column. In part C, we have to calculate a 99% confidence interval for the slope parameter, which is beta, and to do that, we'll simply use the formula given on page 24 of the tables. And the final part is a comment, and to do this, you'll comment on part 3C. We'll observe the confidence interval for the slope parameter does not contain 0, so there is some kind of linear relationship, which coincides with the fact that you should have found there was some association between the age group and the disease. So all in all, a bit of a mixed paper, some trivial questions and some downright confusing questions. But overall, the confusing might have won out, and students would have possibly found this a little bit harder than recent papers. If you wish to chat with your fellow students about this paper, then feel free to post on our forums at www.acted.co.uk/forums.